the fundamental theorem of calculus in 2 and 3 dimensions, curl and divergence. Stokes' theorem measures the rotational force around the boundary of a surface. So we have a surface, normal vector sticking out of it. This induces a orientation on the boundary curve. The boundary curve has the symbol boundary S, that's the symbol we use. There's S. Here's Stokes' theorem, is that the curl of the vector field, I look at the normal component of that over the whole surface, that is equal to the rotational force on the boundary. Curl is a vector that you calculate del cross F. Taking the cross product, partial x, partial with y, partial with z, and then the vectors you're going to take the partial of. Divergence theorem measures the outward flow of the force across a surface. So I have a surface that's enclosing some region. So the region E has a skin, boundary E, and an outward normal. The integral of the divergence over the whole region is the same as the outward flow of the force across the surface. The divergence is del dot F, and the partials dotted with the components. These two theorems are pretty hard to prove, so before going into the proofs, let's just show some examples. First up, we'll illustrate Stokes' theorem. So we'll do an easy surface, a plane, over the unit disk, and a nice easy vector field. Got to calculate the curl, del cross F. Looking at my I component, y partial of x, and the z partial of z. Looking at the j component, x partial of x, z partial of y. Looking at the k component, x partial of z, y partial of y. Minus 1, and minus 1. So my surface integral, curl f dot n ds, minus 1 dot n ds. Parameterize my surface. The domain is over the unit disk, so the natural parameters are x and y. So I want to solve for z in terms of x and y. Or I could use polar. Since it's a circle, that seems like a reasonable choice. X squared plus y squared is r squared, so r is less than or equal to 1. Here's my domain. N ds, I take the cross product of the two tangent vectors, dx dy. Or the cross product of the two tangent vectors, dr d theta. I'll use the standard because that seems like it's going to be simpler. X partial, y partial, cross them, 3, 2, 1. Oh, that is the correct normal. All right. Plug into my surface integral. So I change the domain to the parameterization domain. Do the dot product. -6 factors out. And I'm taking the area inside the unit circle, which is pi. So the whole thing is -6 pi. We can also do it now as the boundary integral of f dot t. So f dot t ds around the boundary. So I need to parameterize the boundary curve. X is cosine theta because r is 1 is my boundary, and z equals 1 minus 3x minus 2y. So I'm plugging r equals 1 into my polar parameterization. One variable, that's a curve. TDS, r prime d theta. So I gotta calculate r prime. Plug in my parameterization. Got to plug my parameterization into my function too. Dot that with r prime. Do the dot product. Dot the third terms. Collect like terms. Sine squared cosine squared turns into a 1. Calc 1 integrals. -2 pi, 0, -4 pi, 0. And -6 pi is my answer. Let's do a divergence theorem. Let's look at a simple example. E is the unit ball. My vector field, x squared yz, minus z, and calculate the divergence. Del dot f. Take the x partial of x squared, y partial of y, z partial of minus z, 2x. So my divergence integral over the volume is the integral of 2x over the volume. Parameterize. Spherical is the natural choice. 3 parameters because it's a solid. Domain, rho less than 1. dv, rho squared sine phi, d rho d phi d theta. Plug in my parameterization. Theta integral, phi integral, rho integral. Now I'm going to do 2x dv. So rho cubed sine squared phi cosine theta. I can break this into 3 integrals because the cosine theta is a constant with respect to rho and phi. It pulls all the way out. All the other integrals have no thetas in them in the limits, so that pulls out. So I can break it up into 3 Calc 1 integrals. And the answer is 0. The divergence theorem is this is the same as taking the outward flow across the boundary. The boundary of the sphere, rho equals 1. Plug that into my spherical coordinates. 2 parameters left, phi and theta, so that's a surface. NDS. Partial derivatives with respect to the parameters, d phi, d theta. And I got to make sure that this is the outer normal. It is. Take my partials. Take my partials. I know it's the outer normal if all the components are positive in this case. I'm looking at the unit sphere in the first quadrant. So the outer normal should be pointing. The outer normal should be positive. So for theta between 0 pi over 2, cross product between 0 pi over 2, everything should be positive. That's positive. That's positive. And that's positive. Plug the parameterization into my function. So now I want to plug my parameterization into the integral. I'm integrating over phi and theta. I dot those two vectors. And integrate. Break it up into 3 integrals. In the first integral, theta is a constant with respect to the phi, so I can pull out. Same with the second, same with the third. So I can break it up into a series of Calc 1 integrals, and we call it done.